Okay, hello everybody and welcome to this week's video in which we will be attempting to derive special relativity from the Maxwell equations. This seemed like quite a fun thing. Again, it's a fairly long one. I'm not sure if we'll get through the whole thing in this video. If not, we'll split it into two parts. That's not really a problem. But yeah, hopefully it'll be interesting. But we'll begin with a bit of preamble. Maxwell came up with his equations in 1865, which is crazy. Like, I hate to sound like an uneducated fool, but it is pretty crazy if you think about it. At least I think, because people hadn't even conceptualized protons, and I mean maybe none of this stuff had been discovered. They were still using the plum pudding model. No one even knows what a plum pudding is anymore. And he discovered this incredible behavior of the relationship between magnetic and electric fields, and they're very elegant and pretty. Now, what was interesting was he found that electromagnetic waves travelled at this speed c, which was 1 over the square root of mu naught eta naught, which is about 3 times 10 to the 8. Now, the concept of relativity had existed since Galilean time, so there was, and it exists in Newtonian mechanics as well. So Maxwell was curious as to, well, he wasn't. Maybe he was curious. I don't know. But then you can be curious. Well, what is this speed relative to? What is it fixed to? So at the time, it was believed that there was no vacuum. This is all nonsense, and they thought that there was the ether, luminiferous ether they called it, which carried light, and that's the speed. And basically that then led to this idea that if Maxwell's equations hold in one frame, they would break in another frame. Now, Michelson, and the famous Michelson-Morley experiment in 1887, found that there was no ether. It found that the speed of light did not change between different frames of reference. Einstein took this very seriously in 1905, and he said that these equations are correct in every inertial frame, and then he came up with special relativity. And I mean, we'll have a look at how that's kind of how you can get that out of the Maxwell equation. So we'll begin with the Heaviside form, that being just the most basic form, no free charges or currents in a vacuum, of the Maxwell's equations. And we're in our reference frame S, which is 4 dimensions, time, and then x, y, and z spatial dimensions. Now, first thing we have to do is derive the wave equation, which is sort of a learny-offy by hearty process. It's not that challenging, I don't think. What we can do first of all is take the curl of the third one, Faraday's law. So we have that the curl of the electric fields. Sorry if my handwriting is a bit bad. I've been using my laptop all week, which has a significantly smaller screen. I've been revising for my exams, and I'm not used to this size, so my writing may be a bit gross. Anyway, this is the curl. I've just pulled that inside. I hope that's not problematic. Everyone can see how that's alright. Then we can take a vector identity on the curl of the curl. We have, then this should become the divergence, that becomes E actually, minus the Lagrangian. Oh, why am I writing? Oh, it's because I'm tilting my tablet the wrong way. There we go. Minus Lagrangian squared E. That's better, less wobbly. And then that's equal to minus. See, my T's are too high because I'm used to going up a smaller distance, or rather a physical distance relates to a small difference on that screen. Anyway, so the left side then becomes Gauss's law, which is this one, which is of course 0, so that goes, and then that whole thing goes, so it's minus squared e is equal to minus gt cross b. And then, well, we can rearrange, or rather, if we just take the second derivative of the final one, Ampere's law, then this is going to be the second derivative, so that's just mu naught epsilon naught. I may have said eta naught earlier, I meant epsilon. I'm really bad at that, and I'm not sure why, because they look completely different. Sorry, dt squared. This is one bit, and then you just repeat the same thing for, then actually you can bring that to the other side, so then it's like that. I'll even rub that out, and take my word for it. B is equal to minus mu naught epsilon naught dt squared, and these are both equal to 0. What was that weird noise that came out of my throat? This is the wave equation, and we can write it in the nice form then by substituting bits and bobs into each other, as follows: squared minus 1 over c squared, that being minus 1 over that, 1 over that squared, because, yeah, squared e over t squared is equal to 0, and the same thing holds for the magnetic field, d squared b dx squared, 1 over z squared d squared e dt d squared b dt squared. So this is beneficial. We have very swiftly derived the wave equation. Now I guess there's the question here: how can we transform? So we want to go from s, which is t x y z, to s dash, which is t dash x dash y dash z dash. I may say prime. I'm not sure why I do that. I think it was a teacher in year 8 that said it's prime, not dash, and I don't know if that either are correct, but I'll try and stick to dash. I'm sorry if I slip. Galilean transformation. Well, we know that t prime is equal to t, x prime is equal to x minus vt, and y prime is equal to y, z prime is equal to z. This is our Galilean transformation from Newtonian mechanics. If you want to derive that, then open any classical mechanics textbook. Now we have to do with partial derivatives. So we can use chain rule. d dx dx prime. Yeah, I'm going to write it in the wrong order. I hope that's okay. That would traditionally would be d dx prime dx prime dx, but that's alright. Plus dt prime dx dt prime equals d dx prime, because things will cancel out, and then for d dt we can essentially do the same thing. I'm not going to write all of this out. We essentially get the same thing, but we see there's minus v dx dash plus dt dash. And so we then also have that the second derivatives are second derivativing. And same for the temporal one. Ugh. Is that squared minus 2v d squared dx dash dt dash plus, this is just partial differential equations. A plus b all squared is a squared plus 2ab plus b squared. And then we can sub things into a wave equation, and we can have the Galilean transformed form, and it's a bit gross. So I'm going to throw the 0 on one side and put the equation on the other side. Over dx squared minus 1 over c squared d squared e dt squared, yep, is squared e dx dash squared minus 1 over c squared v squared de dx dash squared minus 2v d squared e dx dash d, no, that's a 2 t dash. I'm not sure why I'm struggling to do that anymore. It's because it's like near the edge of the tablet. I'm really struggling with this. I need an iPad or something. Or a blackboard is the goal. There we go, and we can pull out 1 minus v squared over c squared. Whoa! Well, look, we're already seeing Lorentzy things. That looks a bit like gamma. Over x dash squared plus 2v over c squared. Don't forget those. Minus 1 over c squared. Yeah, those are gonna need a redo. Just a lot of content, and I'm trying to get through as quickly as possible. Well, importantly here, this isn't the wave equation in S dash, right? We have this cross derivative term, and this modified coefficient of 1 minus c squared over c squared. That means that the speed of light here would appear different in S dash, which is wrong. The wave equation, or the Galilean transformation rather, is actually inconsistent here. So you can't do this. You all got tricked. So instead, I think I did quite a good job. I didn't even allude to that. Now you could see why I was rushing through it. So what do we actually want? Well, let's very carefully put this in a box or something so you can't. There, banned. I should probably make that a bit more straight liney. There you go. So we want in S dash for the wave equation to be true. And for that to equal 0, with c being the same, c not 1 minus v squared over c squared. That's the very important thing here. That's what Michelson and Morley found out, and this is Einstein's second postulate, which is the consistency of the speed of light. So we have to use a different transformation. Well, what are we going to do? Well, we're going to have a new transformation. We're going to have t dash equal to a times t plus bx. We're going to have x dash equal to d times t plus ex. Just because I don't want to get c confused with c. We can ignore y and z because y prime is still y, z prime is still z, z dash is still z, sorry. So let's now do it like this. And what we'd go through here again is the exact same thing as last time. But plugging them back into the wave equation, we're going to get that 0 is equal to e squared minus d over c squared. No, that was terrible. Squared e over x dash squared plus 2 be minus a d over c squared, sorry, over 2 d squared e dt prime dx prime plus b squared minus 8 squared over c squared d squared e dt squared, dt prime squared, sorry. That's a mammoth. Now we need the coefficients to match up here with our this. So, well, the coefficient of if we look at the coefficients of our d squared e dx prime dx dash squared, we have then that e squared minus d squared, that's not a d, that's a p, d squared over c squared is equal to 1. See, why is it all... I hate Wacom. Just making my tablet all annoying-y. I was doing this on the other computer too. Stop complaining. We can look at the coefficients of this, which is just going to be equal to 1. B squared minus a squared over c squared is equal to 1. And finally, be minus ad over c squared is equal to 0 because that doesn't exist. Great. And also 2 does not equal to 0, in case you're wondering that. So this is annoying. Maybe it's a rule in linear algebra. There is a you can't solve for 4 unknowns with only 3 equations relating the unknowns. You need 4. So we need to make a 4. How are we going to do that? Well, if we rearrange and substitute in the dashes and stuff, we can say that at the origin s dash moves with velocity s because they're in the same place. We can call that the world line x dash is equal to 0, to which extent dt plus ex is equal to 0. So x is equal to minus d over et. Now we can solve the system. So if we sub oh no, there's one more. Sorry, one more thing we need to do. The world line is moving at a velocity as well, so we know it's moving at velocity minus d over e in frame s because, yeah, I'm not even gonna. So that must be equal to v then. So minus d over e equal to v. D is minus ve. Now we can solve the system. So if we sub that into our first equation, e squared minus v squared e squared over c squared is equal to 1. Second, I am going to make it pressure more. How exactly does one make it pressure more? Does it feel soft? Hope that's not taken out of context. Okay, good. That looks like it's... That's better. Right. Now we can factor out 1 minus v squared over c squared. This is more like it. To 1, and then e squared equal to 1 over 1 minus v squared over c squared. So e is equal to square root, or rather 1 over square root 1 minus v squared over c squared, which is gamma. Nice. So d is equal to minus v gamma. Now deal with b and ad and b and a rather. So be is equal to ad over c. Subbing things, that should be b. Sorry. So gamma b is equal to a minus av gamma over c squared. B is equal to, we can get rid of that, and yeah, it's just going to be minus av over c squared. And then we can find a squared v squared over c to the 4 minus a squared over c squared is equal to 1 minus 1 over c squared. Whoa, what an equation. Lots of squares. I can put on a squared, that, and then it's going to be v squared minus c squared over c to the 4 is equal to minus 1 over c squared. And then pull that over, a squared is equal to c squared over c squared minus v squared, which is just 1 over 1 minus, divide everything by c squared, so it's just gamma squared. So a is also gamma. Whoa! And b is minus gamma v over c squared. Okay. So now we can actually determine what a Lorentz transformation is. And so, Lorentz transform t dash is equal to gamma t minus vx over c squared. X dash is equal to gamma x minus vt. Whoa! Right, so what we've done so far, little recap, is even in light of my terrible pen, we've successfully derived the wave equation, established that according to Einstein, we need this to, or rather according to experiments done, we need this to be the same in all reference frames. We saw that that is not held in the Galilean transformation reference frame, and then we derived our own reference frame which that is held, which ended up being the Lorentz transformation, the frame of which that applies. Now we can look at some consequences of, and end up with a few interesting things. Again, we may look into this more detail-wise. Actually, I think I might end it here, and then next week we'll look properly into because there's quite a bit left. I've got time dilation, length contraction, velocity addition, space-time stuff with tensors or operators, just operators probably, and then relativistic electromagnetism through the full potential and stuff. Yeah, I think we're going to leave it here after having actually done the thing. It's better than the one I did on the Friedman equations where we didn't actually get to deriving the Friedman. At least I've done the thing in the first episode. But yeah, at that, I hope you've enjoyed. And yeah, I'll be back next week after my first week of exams. Wish me luck. I have history on Russia and the maths paper 1, which is like AS level maths year 1 pure for anyone who's done A levels in the UK. I don't think I don't know, I don't want to jinx it, because year 2 applied is where it's at, that's really giving me a hard time with all the writing and stuff. Who wants to speak English, honestly? Anyway, thank you very much for watching, and I hope you'll join me next week when we look at the physical ramifications of this, what I've shown. So yeah, see you then. Bye bye.